Math 2415, Calculus 3, Multivariable Calculus. Chapter 10, Vectors and the Geometry of Space. Section 1, Three-Dimensional Coordinate Systems. Video 1, Three-Dimensional Space and the Right-Hand Rule. For most people, the section is really pretty easy because by this point in your mathematical career, you should have a pretty good familiarity with two-dimensional coordinate system, normally called the coordinate plane or the Cartesian plane. So we're going to do what a lot of mathematicians do, and what I like to do in my class is to take something that we're familiar with and expand upon it so we can study things in a larger sense. So we're going to start by reminding ourselves some things about two-dimensional space, things that you already know. And if you don't, why are you taking Calculus 3? For example, when we draw a coordinate plane, there is, of course, an x-axis and a y-axis. The x-axis being the horizontal axis, and the y-axis being the vertical axis. Now, it's not necessary to draw them different colors. If you look closely, you'll notice that I did draw the y-axis in blue, and I did draw the z-axis in black. And I'm going to try to be consistent with that coloring system just because. And I did put a lowercase x and a lowercase y on the positive x and y axes, respectively. Of course, the point where they intersect is called the origin right here. And when we have the x and the y-axis, it partitions the plane into 4 quadrants. I think most of you know that quadrant 1 is where both the x and the x and the y coordinates are positive. So maybe I did this a little bit backwards. Let's talk about coordinates real quick. I'm assuming that everybody's familiar with coordinates. For example, if I put 3 marks here on the x-axis and 2 on the y-axis, put a point here on the plane, there is a unique ordered pair that represents that. In this case, the ordered pair would be 3, 2. 3 representing the distance traveled along the x-axis, and then the 2 representing the distance traveled parallel to the y-axis after you've traveled along the x-axis. In other words, over 3, turn and go up 2. Of course, if we have a negative x or a negative y, we would go in the correct direction accordingly. Quadrant 1, of course, is where both x and y are positive. Quadrant 2 is where x is negative, but y is positive. Quadrant 3 is where both x and y are negative, and quadrant 4 is where x is positive and y is negative. So these are the things that you're already familiar with. We shouldn't have to talk too much about them. We can say some other things, such as if you're a point on the x-axis, then your y-coordinate is 0, or if you're a point on the y-axis, then your x-coordinate is 0. Or if you're a vertical line, for example, if you're this line, and we'll put it in pink, I guess, then the equation of this line would be something along the lines of x equals, excuse me, it wouldn't be x equals, it would be y equals, however far down that is, it looks like it might be y equals -2. Or if we had a vertical line, let's put a purple vertical line. In fact, let's drop it right through the point, 3, 2. And if we had a vertical line, then its equation would be something like x equals 3, because all the points on that vertical line have an x-coordinate of 3. In general, if you're parallel to the y-axis, your equation is x equals, and if you're parallel to the x-axis, your equation is y equals. So there's a little bit of a dichotomy there. So how do we extend this into 3 dimensions? Well, let's think about how we build a 2-dimensional space for a second. There's more than one way to label the x and 2 axes in a 2-dimensional space. The most convenient way and the most universal way, when we don't have a reason to do otherwise, is to draw 2 perpendicular lines to each other. And for convenience, we make one of them horizontal and the other one vertical. But if you've taken linear algebra, or if you're going to take linear algebra, you'll learn that we can actually navigate the entire plane with any 2 axes, provided that they are not parallel to each other. And it doesn't matter how they're scaled. There would always be a unique ordered pair to represent that, but I'll save that for a linear algebra class. So if we build a 2-dimensional space, a coordinate system, if you will, by setting up 2 lines that are perpendicular to each other, it would make sense that in order to navigate in 3 dimensions, we would need a third axis, preferably perpendicular to the other 2. Now, how can we possibly draw a third axis that is perpendicular to both the x and the y axis? And the answer is we can't, if we restrict ourselves to 2 dimensions. For 3 dimensions, we have to allow ourselves to come off the screen or off the page. So imagine right here at the origin, there's an axis pointing straight up, and imagine taking a pencil and shoving it through the screen through the origin so that it is both perpendicular. It is perpendicular to both the x and the y-axis. Well, that would be your third axis, and we could intuitively call that a z-axis. So for three-dimensional space, we have an x-axis, a y-axis, and a z-axis. Now, keep in mind, these don't look all perpendicular to each other. This is where you have to realize that we're trying to represent a three-dimensional picture in a two-dimensional surface. So we're not going to be able to draw all three of them perfectly perpendicular to each other. Excuse me. Now, you'll notice that the x and the y-axis are not what they used to be over here. The x-axis was horizontal, the y-axis was vertical, and now the y-axis is horizontal and the x-axis seems to be this diagonal one that's coming off the page. Now, why do we do it like that? Why can't we just draw some z-axis that's perpendicular to both of these? And the answer is it's just a matter of convention. We could orient this three-dimensional these three axes any way that we want. Imagine that we have three axes like this. So we'll say, let me stop the share for a second. So we have, and it's hard for me to do all of these mutually perpendicular. I want to say orthogonal, but we don't know that word yet. So let's just pretend that this is the positive x-axis, positive y-axis, and the positive z-axis. I could rotate these to make them point in any general direction that I want. So it's just a matter of convenience, and it's a matter of being consistent as we move from section to section, chapter to chapter, and problem to problem, and honestly, course to course. It's just a matter of consistency that we orient the x, y, and z axis in this fashion, that the x axis is kind of the one coming off the page. The y axis is horizontal and the z axis is vertical. The way I like to think about it is somebody took this perfectly good two-dimensional coordinate system with the x and the y-axis perpendicular to each other and knocked it over. So it's like a wall that just fell down, boom. And so the x and the y-axis is kind of like the floor, and the z-axis is what's moving upward. Now, why is the positive x-axis over here and the positive y-axis over there? Again, this is mostly a matter of convention. There is a reason why the positive z-axis is going upwards, as we'll talk about in a moment, something called the right-hand rule. But we do have three axes, and they're all perpendicular to each other. It's just hard to draw all three perpendicular relationships in a two-dimensional space, so you have to kind of use some imagination. If you're in a room, however, you can see this. If you look at any corner in the room, then the two lines coming out from the corner on the floor would be your x and y axis. For example, if you looked at one wall where it intersected the floor, that intersection would be an x-axis. If you looked at the other wall where it intersected the floor, that'd be the y-axis. And then the z-axis would be where the two walls intersect. So you can actually look in any corner of a room and go, okay, x and y on the floor, z going up. The origin, of course, is still in the middle, and its coordinates, of course, would be 0, 0, 0. Now, as far as navigating around in three-dimensional space, it's just like navigating around two-dimensional space. You move in the x direction, then you move in the y direction, then you move in the z direction. Now, it's a little bit harder to capture this perfectly every single time because, again, we're representing a three-dimensional space on a two-dimensional surface. But for example, let's say that we wanted to plot the point, oh, I don't know, I'm just making something up here. 3, 4, 2. And let's take the font size up some. There we go. Let's say we wanted to plot this point on this three-dimensional picture. And let's also say that our x and y axis already marked up some. So we'll mark them up here. And we need to go 4 in the positive y direction, and then 2 in the positive z direction. Think of this as a journey from the origin, traveling 3, 4, and then 2 in the correct directions. In this case, traveling 3 in the positive x direction would mean we would have to go this distance 3. And then 4 in the y direction means we would have to go, 4 parallel to the y-axis. So it would look something like this. Now, I'm going to move this just for a second to make sure it's the correct distance. It's a little bit too long, so we'll shorten it just a hair. And now we'll drag it back down here to make sure it's the correct length. And in fact, I'm going to do the same thing with the z-axis, except this time I'm going to go ahead and mark a distance of 2 in the z direction up here on the z-axis and then drag it down here. And then it looks like the point that we would be locating would be somewhere right here. Now it has, oops, hold on. Now, it kind of looks like it's sitting pretty close to the y-axis, but remember that we have traveled this direction on the x-axis, 3 spaces, and then 4 spaces in the y direction, and then 2 spaces in the z direction. So it's actually floating in the air over here above the xy plane. Of course, mind your directions. Negative on the x-axis would go back, negative on the y-axis would go to the left, and negative on the z-axis, of course, would go down. Now, the origin, of course, is where all 3 intersect. That's the ordered triple 0, 0, 0. And it is called an ordered triple because it has 3 numbers, not 2. But we don't have quadrants. We have what are called octants. It's like cutting space into 8 pieces with 3 mutually perpendicular slices. For example, if you're sitting in a room, then you're sitting in one octant. If there's a wall behind you, another octant is behind that wall. There's another octant behind the other wall, and then kind of catty corner from you would be a 4th octant. And then below you, where the z's are negative, you would have 4 more octants. Now, I've looked online, and it's pretty generally accepted that the octants do not have a numbered system like the quadrants do. The quadrants are 1, 2, 3, 4. That's fairly universal. There's only one octant that is actually called the first octant, and the first octant is where both x, y, and z are all positive. So in general, the only octant with a specific name is the first octant. And that's where x is greater than 0, y is greater than 0, and z is greater than 0. We can refer to the other octants based on whether or not their x's are positive or negative. For example, if I wanted to say x was positive, but y was negative and z was positive, then I would be going positive x, negative y, positive z, and I would be up in this corner over here. But I'll rarely refer to any of the octants by their name besides the first octant, where both x, y, where all of x, y, and z are positive. All right, last thing I want to talk about is something called the right-hand rule. I don't worry too terribly much about this in this math class, even though there is going to be a lot of physics and engineering flavor to a lot of the stuff that we do. And in physics and engineering, the right-hand rule is used quite a bit to resolve some issues in terms of the directions that certain vectors point. We don't know what a vector is technically. It's pretty common to introduce it here to talk about the orientation of the axes. The right-hand rule kind of goes something like this in terms of setting up x, y, and z axis in 3-dimensional space. If you curl the fingers of your right hand, I know this looks like my left hand, but it's my right hand when I'm looking at it. If you curl your right hand around the z-axis in the direction of a 90 degrees counterclockwise rotation from the positive x-axis to the positive y-axis. So in other words, grab the z-axis with your right hand so that when you curl your fingers around, you hit first the positive x and then the positive y. Then the direction of your thumb is the direction of the positive z-axis. Now, this is represented. There's a good picture of it. Let me see if I can find it here. That's not it. I'm about to share it with you because I don't want to share the screen until I know that we're looking at the right thing. Right-hand rule, right-hand rule, right-hand rule. The picture I'm about to show you actually comes from the textbook. I think I zoomed too far. Here it is. Okay, now let me share this with you guys so you guys can see this. All right, new share. Here we go. This is from the E version of the textbook available in the Canvas class that I'm currently teaching. But if you were to take your right hand and wrap it around the z-axis so that your fingers wrap around the positive x-axis and then the positive y-axis, then the direction of your thumb is where the positive z-axis is. If you're interested in some more uses of the right-hand rule in physics and engineering, I would recommend the following Wikipedia page. You just go to Wikipedia and search right-hand rule, and you'll see this. And on the contents over here, there's a lot of physics and engineering applications that they talk about, some of which I really don't have much of an idea about. As I tell my classes all the time, I'm a mathematician. The only physics and engineering I know is the physics and engineering that I incorporate in the math that I teach. But for those of you who are more familiar with physics and engineering topics, you may be able to read some of these applications and go, okay, I've seen that stuff before. And a lot of these things are things that we are going to incorporate in our multivariable calculus class, our Calculus 3 class. All right, and I believe that wraps up this first video.